Now, to go back a bit to string theory, can I say again, the different ways in which the strings and the loops of string vibrate should correspond to the different particles of the standard model, the fermions and the bosons. And the great hope was that when they worked out the string theory and worked out the frequencies of these string vibrations, they would come up with numbers that corresponded to the standard model and explained it all on the basis of strings. They did find 5 distinct versions of string theory which were all sort of mathematically consistent. They all solved the problems, the infinities disappeared and so on. But none of them gave answers that agreed with the standard model. So far string theory has been a failure in the sense that it has not predicted, it has not united the particles of the standard model. It has some wonderful mathematical successes, but it's not explained the physics that it set out to do. There is, of course, a problem with these extra dimensions. We've got 9 dimensions of space in string theory. We know that we live in a 3-dimensional world, so what's happened to the other 6 dimensions? Well, the idea is that they get wrapped up very, very small, so you can't see them. Throughout space, the other 6 dimensions are believed to be sort of wrapped up on each other at a very, very small size, and they are completely invisible to normal things. This is the space in which the strings move, but we can't see it. It's called compactification, making the other dimensions compact. Now, here are 2 very basic difficulties with string theory, apart from its failure to explain the standard model. One is, we've got 9 dimensions, why should we wrap up 6 of them to leave 3 large ones? Why not wrap up 4 of them and leave 5 large ones, or wrap up 7 of them and leave 2 large ones? What explains why we're in a 3-dimensional world? Well, nothing. In other words, there's nothing in the theory that says this is why we live in a 3-dimensional world. You may say, by the way, it could be the other way around. Everything started very small, and then inflation happened, and just 3 dimensions expanded, leaving the rest very, very small. That would be an alternative way of doing it, but it still leaves the question, well, why just 3? Why do we live in a 3-dimensional world? String theory has no explanation. That's pretty fundamental. Now, second major problem, even if you decide, okay, we're going to wrap up these 6 dimensions and leave 3 large ones, turns out there is an incredibly large number of ways of doing it. Not just one. It would be nice if there was just one simple way of wrapping up the unwanted dimensions. But it turns out that the number of doing it is the biggest number I've talked about so far in these lectures. This is one followed by about 500 zeros, which is a ridiculously large number. Okay? And there's all of those different ways of wrapping up the extra dimensions, and each one would give rise to a different set of physics, a different universe. Okay? That is a bit of a problem. Before we go on talking about the bit of a problem, I should say something about M theory, which is really a development from string theory, which is more complicated, as if string theory wasn't complicated enough already. It assumes, instead of just strings, membranes of different dimensions, 2-dimensional membranes, 3-dimensional membranes, 4-dimensional membranes, lots of different dimensions of these extra things called branes or membranes, and they live in 10 dimensions of space instead of 9, extra dimensions still. The idea, the claim is that actually the 5 different versions of string theory are all special bits of M theory. M theory is supposed to be an all-embracing theory where the particular types of string theory appear in one or other version of M theory. So people are very excited about M theory. This, if you've read Stephen Hawking's book, this is where he finishes up, talking about the wonders of M theory. But it is not yet a definite mathematical theory. You tend to think, I tend to think, of a mathematical theory as a set of laws with equations that you can solve. There ain't no equations so far in M theory. It's just a very subtle idea. I think it's more like a very exciting program of research than a theory. Okay? So that's roughly what M theory is. It's very closely related to string theory, and I think the simplest thing is, from now on, when I say string theory, I really mean string theory plus M theory and all its ramifications. Okay? So if that's what string theory is, what has string theory got to do with the multiverse? Well, first of all, here is a possible way of getting different laws and constants of physics, and in fact, different histories of the universe. All these different versions of string theory will naturally have different laws of physics. So here is a possible way of getting a whole lot of different laws of physics. They would also have what's called the vacuum energy, which I see I've misspelt. The vacuum energy, or the cosmological constant, the thing that causes inflation, causes acceleration. Each of these different versions of string theory could have different ways of causing rapid inflation. Third thing is to tie it in with an idea called eternal inflation. I talked about the strongly favoured idea, though it's still very hypothetical, that right in the first instant after the Big Bang, there was a very rapid inflation by huge order of magnitude over a tiny period of time called inflation, which explains a number of things. But a number of cosmologists actually think inflation has never stopped, and that you have an inflating universe within which other universes inflate, and inside other, the whole thing is going on eternally. And by the way, if each period of inflation only lasts for, in mathematical terms, 10 to the minus 32 seconds, which is a millionth of a millionth of a millionth of a millionth of a hundredth of a second. That's about how long inflation is supposed to have lasted in our universe. You may think, well, it's going to be over pretty quickly, isn't it? But not if there are 10 to the power 500 different universes. So eternal inflation is bubbles within bubbles within bubbles, continually going up. So, fourthly, if what we have in these two things is, first of all, a way of having different laws of physics, and secondly, a way of actually generating universes by eternal inflation, which would have different laws of physics. Do you follow me? So, a way of generating universes, a way of generating different laws of physics. And, by chance, one of them could possibly have the right laws of physics. For example, the right cosmological constant. It's worth actually saying that the thing that finally convinced Leonard Susskind that there was something funny going on, that there really was the appearance of design, was not water or life or the carbon resonance. It was this cosmological constant. The fact that a number with 200 zeros was so nearly zero but not quite one, not quite zero. Anyway, by chance, one of these infinite or almost infinite number of universes could have the right laws of physics, and there are lots of them. 1 to the power of 500 suddenly becomes an asset rather than a liability. There's enough different ways of doing it that you're not sort of beaten by the laws of chance. Which is what this diagram that I had at the beginning is supposed to be. This is bubble universes. Okay, I mean, clearly you can't really have any proper picture of them, but the idea is that each bubble is a complete universe. Some of them are inside others, others are quite separate, and they expand very, very fast because of inflation. And in fact, because they expand so fast, if you're inside one of them, it actually looks infinite. In other words, you can never see out of it. The edge of the bubble is going away from you so fast, like the speed of light, that you can never see the edge of the bubble. So you think you're in a universe. Do you follow me? The only thing you might possibly see is if two of these bubbles collided, you might see some rings or something where the collision took place. But in principle, it's virtually impossible from inside one universe to see another bubble. How on earth are we going to assess this multiverse idea? I do think we have to take seriously the fact that it is quite strongly favoured by a large number of very competent scientists. Some of the most brilliant brains in physics and cosmology at the moment think this is a good idea. They like string theory and they like the multiverse. So, Stephen Hawking is perhaps the most well-known, who is now favouring it. Leonard Susskind is the person who, probably more than anybody else, invented string theory. He is a very, very competent scientist, and he is strongly in favour of this. Martin Rees, who was President of the Royal Society, Astronomer Royal, he's now Master of Trinity College, very, very competent cosmologist, and he's been favouring the multiverse for a number of years, and I think is quite open to the idea of the string theory multiverse. So, a lot of very, very good scientists think this is the bee's knees, think this is the way to go, think this is the explanation. Although, even within the scientific community, there are people who strongly object and think this is a lot of rubbish. But I mean, it's worth saying that there are objectors, but many competent scientists favour the idea. Some difficulties in assessing this multiverse idea. The first one is the difficulty, maybe the impossibility of actually doing an experimental check. In other words, we are within one universe with a set of laws of physics, and we can observe them. If it is in principle impossible to see any other so-called universe, then we can never ever check that there are other universes. That's a serious problem in principle. It would be more convincing if there was some experimental evidence showing that string theory was correct. I'm supposing that somebody had produced a version of string theory which explained the standard model. Say, if you do it this way and wrap up the equations this way, then we get the numbers out right. You say, oh, that's pretty convincing. Maybe string theory is right. Maybe the multiverse is right. But at the moment, string theory has not succeeded in that sort of way. There is a further problem, which is this. There are so many possible versions of string theory, 10 to the power 500, you can never prove it's wrong. Because someone can always say, well, we can just change the numbers. There's so many other ways of doing it that you could never ever say string theory is disproved. Because you can always think of another version which would be different. Do you follow me? It's worth saying that all this string theory is supersymmetrical. It does predict SUSY. And SUSY has not been seen. So if, for example, when they bump up the energy of the Large Hadron Collider by a further factor of 2, and we still don't see supersymmetry, it'll get a bit more difficult. So, you know, the observation of supersymmetry would not prove string theory. There are other theories which are supersymmetrical apart from string theory. But if you disprove supersymmetry, you disprove string theory. I think it's worth saying that we should possibly apply Occam's razor. Anyone heard of Occam's razor? It's a sort of a philosophical principle which is quite hard to tie down precisely, but the general idea is that you prefer a simple explanation over a complicated explanation. Don't unnecessarily multiply hypotheses. So if in order to explain something you have to have this, this, and this, if all these 10 things were true, then we could explain it. And someone else comes out and says, but I just have 2 things, and that explains it. You generally would go with the 2 things rather than the 10. Now, I think it can be claimed that string theory and the multiverse is an awfully complicated explanation of design. In other words, to have 10 to the power 500 universes, and this incredibly complicated, it's all amazingly complicated. And in a sense, I think Occam's razor is not a disproof of string theory, but I think it might be worth applying it. We would prefer a simpler explanation to this very complicated explanation. Maybe the explanation is more complicated than what it's trying to explain. If you want a critical point of view about string theory, then there's a book by Peter Voigt called Not Even Wrong, which is, I may say, quite technical, and a website with the same name, Not Even Wrong, which I would recommend. Perhaps I should explain where the phrase not even wrong comes from. There was a very famous physicist called Pauli, and apparently he was a nightmare if you were giving a physics seminar and he was in the audience, because you would say something and he would say, falsch, or in German, wrong, or ganz falsch, completely wrong. You know, he was a very, very good physicist and he was very critical. And one of his students came to him with a piece of research that he'd done. And Pauli said, apparently, rather kindly, said, I'm sorry, it's not even wrong. It doesn't attain the status of something that could be disproved. And Peter Voigt thinks that string theory is in that category. Here then is my own opinion of string theory. I think it is a very deep and subtle set of ideas, but until or unless there is experimental evidence for string theory at least, I am unconvinced. It seems to me that the very essence of science is you take experimental verification very seriously, and you don't allow theories to be spun too far without being checked experimentally. You see, I've been talking about the standard model of particle physics and the standard model of cosmology. These are both theoretical ideas, but in both cases there is a vast amount of careful, numerical, quantitative, experimental evidence. Doesn't prove that they're true, but if you get lots and lots and lots of evidence that agrees with things, you tend to think, well, it's probably true, okay? String theory is in a completely different case to the multiverse. There ain't no evidence at all. And until there is evidence for it, I remain a little unconvinced. Can I give you two lessons from the history of physics? And the first one is called the vortex ring model of the atom, which very few people have heard of, but I came across when I was writing a series of notes for physics teachers on the standard, on higher physics. And I discovered that towards the end of the 19th century, the late 1800s, this idea of the vortex ring model of the atom was put forward. Here's a smoke ring being produced with a sort of box that you bang and out comes a smoke ring, quite a big one. The smoke is just making the vortex visible. It's actually just a ring of rotating air, okay?